What exactly is a magnetic dipole? You would have often seen, you would have often played with a magnet. Have you ever wondered what will happen if you break the magnet into different parts? Will you still have a north pole and a south pole in it? Let's now try to understand about this in our next part, that is magnetic dipoles. So let's now move on to the magnetic dipoles. What exactly is a magnetic dipole? When we talk about a magnetic dipole, or for that matter any dipole means two charges. So you should have equal and opposite charges, right? That means both the charges should have the same magnitude and the signatures should be different. Further, the charges are going to be kept at a particular distance away from each other. That is what we call a magnetic dipole, or for that matter a dipole. When we are talking about a magnetic dipole, it is nothing but you have a north pole and you have a south pole. That is, any magnet will always be in the form of a dipole. Unlike in the case of electric charges, wherein you can necessarily have a positive charge separately and a negative charge separately, kept at a particular distance as well, or as well as separately. But if you are talking about a magnet, in the case of a magnet, you will always have one or the other, north pole and south pole both being together. You cannot have them separate. Now let's try to understand that. So when we try to talk about a magnetic dipole, so a magnetic dipole has two polarities, one a north pole, other one a south pole. You can, because so far we have only understood it in terms of a current loop. So when you have a current loop, because of a particular direction of the motion of current, you can either have a south pole or a north pole being produced. So, but we understand the polarity of the magnetic dipole due to the current loop. So, if you now look at one of the phases that you can see of the coil, the direction of current through the coil is in a clockwise direction, as you can see. This goes like this. Therefore, that results into a what is known as a south pole, like you can see it here, the directions. And if you reverse the direction of the current, that is it, the current is in an anti-clockwise direction, then the phase would have a north polarity. Now let's move on and try to talk about what is a solenoid. So what exactly is a solenoid? You have a group of wires through which you have the magnetic field lines passing through. So this is what is known as a solenoid. So if you have to define it, so it is a long coil of wire which consists of closely spaced loops. So you have the loops through which the current is flowing, and therefore the magnetic field lines are going to be crisscrossing the main body of the solenoid. Magnetic field due to the solenoid resembles to that of a bar magnet, because you have the field lines passing in a circular, or the current passing in a circular way, and therefore you will have the magnetic field along a particular direction. So that is going to tell you that since if it is going from a particular direction to a other direction, so within that you can say that from where it is actually coming out, that is the north pole, from where it is going in, that is the south pole. So this resembles actually a magnet or a bar magnet. The net magnetic field of a solenoid, how exactly are going to find it out? Because these are all vector components. The magnetic field that you have is nothing but vector. So you have to find out the vector sum. So when you try to find out the vector sum, that's going to give you the net value of the magnetic field. Moving further, the magnitude of the magnetic field inside a long solenoid is going to be given simply as B equals to mu naught Ni. So this can simply be found out by integrating over. If you have a long enough coil, so what exactly you can do here is that if you have a long enough coil like this, you are trying to find out the magnetic field here. So what you will do, you will take a small region here which will have a length dl, current flowing through this is I. I'm just referring to the Biot-Savart's law, and let's say r is this distance, this is making an angle theta with this. So this tells you as to how much is the magnetic field. Let's say this is your point P, so how much is the magnetic field B. So dB, you know, is going to be given by mu naught by 4 pi, and then you will have I dl sine theta over r square, correct? So this is the value of the magnetic field. So once you integrate, so you need to integrate, if you are integrating it, if it's a long solenoid, for the case of a long solenoid, what you are going to do, you will say that this is what we have, your point is somewhere here. So you are extending from this to this. So effectively, the angles that you have, angles are going to be such that one point is 90 degree, other is going up to infinity, and that results into the net value of the magnetic field, which is given by this particular formula. Moving on, if we talk about a long air core solenoid which does not have any other material cladding within the core, or within the core there is no other material, so it does not have any dielectric constant. So if you are required to find it, how exactly you are going to do that? You see that this is the cladding through which the current loops are actually going to be like this. Now you take a cross section here and you take a cross section within it and one outside it. Okay. So if you have to find out, the total, how much is the amount of current or the magnetic field over a particular length. So what we are going to do, we'll try to find out B dot dl because of this particular current element. Therefore, we'll have B dot dl here. This is from P to Q. So let me just change the color so that it makes sense. So once is from P to Q, then we have from Q to R, then we'll have from R to S, and from S to P. So this is going to complete the whole circle. You can see that from P to Q, this is within this length. Okay. So if I say that this length is L and here there is a magnetic field produced. So magnetic field is B and dl is the length of the path. So B dl is along the same length. So you can simply say that this is equal to BL. For this particular part, the magnetic field and the lengths are perpendicular, and so will be for this part. So therefore, B dot dl is going to be 0. Further, outside this region, there is no magnetic field. So as a result, what will you get? The net value of magnetic field B dot dl, which is going to be within it. So the field outside the solenoid is going to be equal to 0. Using this, what will we get? Since this is equals to B into L, as we just found it out, but B into L is nothing but mu naught into I. This is what is the Ampere's circuital law, which we already know. So if I am saying that this is equal to the Ampere's circuital law, so what do I get as a result? I'll simply write it as mu naught into Ni, just cancelling out all the remaining factors. So I'll get B equals to mu naught into Ni. Now what do we have here? B depends on N and I. So what does N stand for? N is nothing but the number of turns in that particular solenoid, and I, it's independent of the position where exactly you are trying to measure the magnetic field. It is independent of that. So the field inside the solenoid is going to be completely uniform. There is not going to be any non-uniformity in that. Further, if the solenoid is iron cored, means if within the solenoid you have an iron core in that case, what we are going to do, we'll say that B is going to be equals to mu into Ni. So that is what is going to be our net result. Here, mu r is what? Mu r is the relative permittivity of this core that we have. Further, when you are talking about the near ends of the solenoid, when you are not going so far away, so that is going to result into the field which is nearly half of the total. Uniformly, if you are talking about, it is mu naught Ni, and near the ends you will say that it's equals to half mu naught into Ni. Okay, now you had a solenoid like this. Now if you just join the two ends of the solenoid, that results into what is known as a toroid. So this is what is the expression of a toroid. So you have the current entering from here and leaving out from here as well. So you have the current loops passing through this. The magnetic field is going to be in this particular part. So it's going to be in a circular path at this particular point. So if you want to find out what exactly is the magnitude of the magnetic field B, so for that, what we are going to do, first of all, let's try to understand what exactly constitutes a toroid. A hollow circular ring on which a large number of turns are closely wound. So you have a large number of turns being wound of this particular solenoid. It can be viewed as a solenoid which has been bent into a circular shape to close on itself. So there are no open ends. Like in the case of solenoid, there are no open ends here. For this case, the magnetic field B is going to be given by mu naught Ni divided by 2 pi r. Why 2 pi r? Because it's also going to depend upon how much is the radius from the center. Why? Because longer is the radius, farther away it's going to be, and therefore the magnetic field is going to decrease as a result. So what we are going to have in this case, this is going to be the path that is going to be followed by any electron or any charge carrier within it, and as a result you will get the net, using the Ampere's circular law, the net magnetic field within a toroid is going to be given by this particular formula. Hope you understood till this point. We understood that in this part that when you break up a magnet, it is still going to be breaking up into two different parts. That is, north pole and south pole are always going to be together. Unlike in the case of electric dipoles, where you can have standalone the negative charge and a positive charge. In this case, you will always have a composite positive and negative charge standing together. That is what is a magnet. So a magnet always has a positive pole and a negative pole. That is what is a magnetic dipole. Now, if we try to generalize that and we have charges or currents that are flowing in a particular manner, that results into a current loop. And within a current loop, if you have magnetic field lines going in a particular direction, that results into what is known as a solenoid. We understood about the solenoid. But we saw that a solenoid has open ends. You have two open ends. Supposing you join those open ends, you get what is a toroid. Right? Hope you just understood about this. Now, we'll try to generalize this for the case when you have two current carrying conductors in which you have current flowing through them either in parallel or in anti-parallel directions. We'll try to understand about how much is the force that acts in them.